A screening model examines 1,000 patients. 20 truly have the condition. At this threshold, the model catches 15 of them, misses 5, and raises 45 false alarms. Its accuracy is 95%. That sounds excellent. Until you notice that only 1 in 4 positive alerts is correct. The same classifier is 95% accurate, 25% precise, and 75% sensitive. Nothing changed except the question. To understand why, begin with 4 outcomes, not formulas. A true positive is a real case the model flags. A true negative is a healthy patient it correctly clears. A false positive is a false alarm. A false negative is a missed case. Put those 4 counts into a confusion matrix. The word confusion does not mean the model is confused. It means the table compares predicted labels with actual labels. Every threshold-based metric simply chooses a different part of this table to emphasize. Accuracy asks, what fraction of every decision was correct? Add true positives and true negatives, then divide by everyone. Here, 950 correct decisions out of 1,000 gives 95%. Accuracy is useful when the classes are reasonably balanced and both kinds of mistake carry similar cost. But with only 20 positive cases, the 935 correct negatives dominate the score. A model that predicts negative for everyone would still be 98% accurate, and would miss every patient with the condition. Now, ask narrower questions. Precision begins with the model's positive alerts. When it says positive, how often is it right? 15 correct alerts divided by 60 total alerts gives 25%. Use precision when acting on a false alarm is expensive, perhaps a manual investigation, a blocked payment, or an invasive follow-up. Recall begins with the actual positive cases. Of everyone who truly has the condition, how many did the model find? 15 out of 20 gives 75%. Recall matters when a missed positive is costly. In medicine, it is also called sensitivity. Specificity mirrors recall for the negative class. Of all actual negatives, how many did the model correctly reject? Here, 935 out of 980 is about 95.4%. Precision asks whether alerts are trustworthy. Recall and specificity ask how completely each real class was handled. Sometimes, you need one number that becomes high only when both precision and recall are high. The F1 score takes their harmonic mean. With 25% precision and 75% recall, F1 is 37.5%. The harmonic mean punishes an extreme imbalance between the two. But F1 is not automatically the right answer for imbalanced data. It ignores true negatives, and ordinary F1 gives precision and recall equal importance. If missing a case is 10 times worse than investigating a false alarm, that equal balance does not describe your real decision. These 5 scores describe one threshold. Move the threshold lower, and more patients are labeled positive. Recall usually rises because fewer real cases are missed, but false alarms also rise, and precision may fall. Raise the threshold, and alerts become rarer. Precision may improve, while recall falls. There is no universally best threshold hidden inside the model. Choose an operating point from consequences and capacity. How many misses can you tolerate? How many alerts can a team review? And what does each error cost? Then report the metrics at that actual operating point, not only at a convenient default of 0.5. What if you want to compare ranking ability before committing to one threshold? Record recall, the true positive rate, against the false positive rate at every threshold. Those points trace the ROC curve. Its area, ROC-AUC, summarizes how well the model tends to rank a random positive above a random negative. 1 is perfect ranking. 0.5 is random-like ranking. ROC-AUC is useful for comparing broad ranking behavior across thresholds, but it averages over operating regions you may never use, and it doesn't tell you which threshold to deploy. A strong AUC can coexist with an unacceptable number of false alarms at your chosen point. When positives are rare and positive alerts are the operational focus, view the same threshold sweep in precision recall space. The curve shows how trustworthy alerts remain as you try to capture more real positives. Its summary is often called PR-AUC. Libraries may report average precision, which is related, but not always numerically identical to every area calculation. Unlike the random ROC baseline of 0.5, the precision baseline follows the positive prevalence. In this cohort, that is only 2%. This sensitivity to prevalence is useful when the test set reflects deployment, but it also means scores from populations with different class mixes are not directly comparable. Use a representative test set and inspect the curve near the recall you actually need. So far, a probability of 51% and 99% produce the same positive label. Log-loss sees the difference. It scores the probability assigned to the true class and sharply punishes confident mistakes. If a positive case receives probability 0.49, the model is slightly wrong at a threshold of 0.5. If it receives 0.01, the model is confidently wrong, and the penalty is far larger. Use log-loss when probabilities themselves drive ranking, pricing, or downstream decisions. Lower is better. But probability quality also deserves a calibration check. Predictions near 70% should be correct about 70% of the time, in comparable cases. So, which metric should you use? If classes are balanced and errors cost about the same, accuracy is a useful overview. If positive actions must be trustworthy, prioritize precision. If misses are costly, prioritize recall. If false alarms among negatives matter, inspect specificity or false positive rate. Use F1 only when its balance and omission of true negatives fit the problem. Use ROC-AUC for broad ranking across thresholds, and a precision recall view when rare positive retrieval at representative prevalence matters. Use log-loss when probability confidence matters. Then choose a threshold from real costs and report more than one view. The best metric is not the one with the largest number. It is the one that makes the consequence of being wrong visible.